Have you had a chance to think about how you can demonstrate that the Earth actually moves around the sun rather than everything else moving around the Earth? Now I'm going to give you a hint if you haven't been able to figure out. Now look what I'm doing now. I'm moving my head back and forth, and I can see my finger seems to be moving back and forth against the wall that's out at a distance. And if that's so, then if the Earth is moving around with respect to inertial space, here we have the Earth going around the sun, and if you look at a nearby star with respect to faraway stars, just like moving my head back and forth, we should see stars, some stars at least, over the course of a year, moving back and forth in the heavens. And this is called stellar parallax. And in fact, you can see from the geometry here, if we know the size of the Earth's orbit and we can measure this angle, then we could actually determine the distance to that star. And this is very important because, in fact, this is the beginning of the development of the astronomical distance scale, which has taken us out to billions of light years away from the Earth. But the closest stars, we can measure their distance by stellar parallax. Well, the great astronomer Tycho, who was able to make very, very accurate observations of the positions of stars and planets, he didn't have a telescope. He had essentially a big sextant or a protractor, and he could measure down to about 1 minute of arc. That's 1/60th of a degree, and he didn't see any stellar parallax. He appreciated that if Copernicus was correct, he should have seen it, but he didn't. And as it turns out, Tycho was a good scientist. He followed his data and he drew the conclusions that he had to, which was that the Earth was not moving to the limits of his observations. And he wasn't just guided by some theoretical idea that he was trying to prove. He based his ideas on his data. Well, it turns out, we know now, that even for the nearest star, Alpha Centauri, the stellar parallax is only about 1 second of arc, which is 1/60th of a minute, or 1/3600th of a degree. That was an order of magnitude smaller than Tycho's best observations. And so Tycho was, I think, justified in not accepting the Copernican theory. But his student, Kepler, who had worked with him when Tycho died, took over Tycho's observations. And Kepler wanted to be able to develop a mathematical concept of the motion of planets. And Kepler believed in the Copernican theory. He was working at a time when modern science was just evolving out of the sort of philosophical, mystical traditions of the Middle Ages. And just like the Greeks originally wanted to explain planetary motion in terms of perfect circles, Kepler worked for many, many years, a couple of decades almost, trying to use geometrically perfect solids to explain planetary motion. He was very frustrated. He couldn't get it right until finally he came up with the brilliant insight that if he didn't use these perfect figures of circles or geometrical solids, but instead used ellipses, then he could actually do a good job of explaining and predicting planetary motions. And this is how we're now going to get into Kepler's laws, to look at Kepler's great insights into the motion of planets. And he had 3 famous laws which we're going to discuss briefly. The first law, and of course Kepler did all of this before Newton's theory of gravitation. If 2 bodies are interacting, then they will describe orbits which are what we call conic sections about the common mass of the pair. Now, if one of the objects, like the Earth and a satellite, is much larger, then we can look at the large object as being the center of the orbit, but the shape of the orbit will still be a conic section. And what's a conic section? It's the intersection of a plane with a cone, and we can see here, if the plane's angle is just right, we'll get a circle, but a more general situation, we'll get an ellipse. If we keep tilting that plane so that it's completely parallel to the side of the cone, we'll get a parabola, and if we keep going, we'll get what we call a hyperbola. Parabola and hyperbola correspond to what we call open orbits, when the two objects are not gravitationally bound. Circles and ellipse are gravitationally bound orbits. So what Kepler's first law is telling us is that planetary motion in our solar system, and of course this can be generalized to gravitational motion in general, but planetary motion takes place in ellipses. The orbits of planets around our sun are ellipses. In order to understand some of the consequences of this, let's look at a little more detail at what actually constitutes an ellipse. So we're not going to go deeply into the mathematics of ellipses, but I thought it would be interesting to show some basic principles of ellipse geometry. How do we make an ellipse? Well, an ellipse has two focal points, which I've indicated here with two thumbtacks, and then we can take a piece of string. This is a standard length, and I'm going to put it around the two thumbtacks. And now what I'm going to do is to take a marker and draw it such that basically the distance from one of the tacks up to the edge and back stays the same. So I'm going to put this in, and now this is going to give me an ellipse. And notice we have two focal points. These are the foci of the ellipse. And for planetary orbits, at one of these foci would be the central attracting point, such as the sun, and then you might have a comet or some other eccentric orbit object going around like so. Now, the degree to which this ellipse is non-circular we refer to as the ellipticity or eccentricity of the ellipse. And look what happens if I bring the two foci a little closer together. Here we go. I will do the same drawing. Still we'll have an ellipse. But notice now it's a lot less eccentric, more nearly circular. And finally, if I bring the 2 points together, what we'll have is actually a real, honest-to-goodness circle. And so we can see that the circle is essentially a special case of an ellipse. And the critical elements for the ellipse are, first of all, the size. That is, this is called the major axis of an ellipse. And if we take half of that, it's the semi-major axis. And that's what we use to refer to the size of the ellipse. And of course, for a circle, that semi-major axis is just the radius of the circle. So that's the first thing, is the size of the ellipse. And the second is the ellipticity. In other words, is it circular, in which case the eccentricity or ellipticity is 0. And actually, we could take a special case here and put it in where, in this case, we have a very, very flat ellipse with a ellipticity approaching 1. And in fact, if I continued this and stretched it out all the way, I'd get almost a flat line. It's hard to get around the thumbtack there. So you see, we can vary the shape and the size of the ellipses, and all of those will impact the actual orbit of the satellite going around the object. So with this basic introduction to what an ellipse is, we'll proceed with our discussion of orbital mechanics. Okay, so now I think you understand that a circle is just a specialized case of a more generalized ellipse. And for the next part of the demonstration, I'm going to get rid of the ellipse because it's a little bit ungainly to work with, and I'm just going to use the circular orbit. But what I want to show you is the other implication of Kepler's first law, and that's that the plane of this orbit has to intersect the center of the Earth, or the Sun, or whatever object you're orbiting around. So here we would have a satellite in orbit over the equator of the Earth, and that's perfectly okay. The plane intersects the center of the Earth. Here we're going over the two poles, but again, the center of the Earth is in this orbital plane. This, on the other hand, is not a legitimate orbit because the plane of the orbit goes over the northern hemisphere. It does not intersect the center of the Earth. So legitimate orbit, this is not an orbit, and this is all what comes from Kepler's first law. So we see with an elliptical orbit that, for instance, if this is the central body here and we're moving around, that sometimes we're closer and sometimes we're farther away, and this is characteristic of planetary orbits. When we look at the moon, actually it turns out that the moon's orbit around the Earth is slightly elliptical, and sometimes when we get a full moon, the moon is at its closest point, and sometimes the moon is at a farther point. So to the left here, we see what sometimes the newspapers call a supermoon, when the moon is as close to the Earth as it ever gets in its orbit. And on the right, we can see when the moon is farther away. So this is an actual illustration of the ellipticity of the moon's orbit. And it has an effect when we look at solar eclipses, because every once in a while, the moon passes between the Earth and the Sun and blocks out the Sun, and we get these spectacular solar eclipses. When the moon is relatively far from the Earth, as we see here on the right-hand side, then it doesn't block the entire disk of the Sun, and we get what we call an annular solar ellipse, or just a little ring of the Sun is still visible. But fortunately, most of the time when the moon passes between the Earth and the Sun, it's close enough so that the lunar disk covers the entire disk of the Sun, and we get treated to a total solar eclipse, which is one of the most spectacular celestial phenomena that you can ever see.